Okay, so in this video, we're going to talk about calculating using the Gauss elimination method in Python. So let's first talk about what our goal is. Our goal is to take an augmented matrix, an n row by n plus 1 column augmented matrix as input, and use Gauss elimination to either find a unique solution or halt it if we have an arithmetic error. Okay? Now let's decompose the steps a little bit so that we can kind of break down what needs to happen. First thing we're going to do is we're going to prompt the user to enter the number of unknowns. After that, we're going to establish an empty container, an n by n plus 1 matrix that's full of zeros. That's going to serve as a container for the step after the next. We're also going to establish a zero vector of size n to be a container for the solutions. Now that might seem a bit strange because after you go through Gauss elimination method and once you do back substitution, the solutions begin to form in the right-handmost column of the augmented matrix. But we're also going to reserve an extra vector. That's a new word too we haven't talked about yet. Think of a vector as just one column of the matrix. And so this vector is a one-column matrix that's going to hold the solutions. We're going to create that in extra, and we're going to fill it with zeros as like a container temporarily. And we'll start adding in the solution values later on. Then we're going to prompt the user to enter the matrix coefficients one column at a time. This is when we begin Gauss elimination algorithm. If we encounter any zeros on the diagonal, we're going to halt the program. There are stronger ways to program it so that you can actually swap rows if you accidentally encounter a zero, because sometimes a row swap would be helpful, but we're not going to make our program that smart. This is basic, very basic, and so if we encounter any diagonal element of zero, we just halt the whole thing. Once we've completed GEM, we're going to begin backwards substitution if the program has not halted, and then we print the solutions, end of program. So okay, let's now get into Gauss elimination method using Python. You're going to need these two packages. We're going to import numpy, we're going to rename it np, and we're going to import the system package. And then right here, lines 4, 5, and 6, line 4 prompts the user to enter the size of the matrix, or the size or the number of solutions. This creates a matrix, an augmented matrix, line 5, full of zeros that have n rows and n plus 1 columns. And this creates our vector full of solutions, but right now the solutions are all zeros, so lines 5 and 6 are our containers. Now, if you've never programmed before, this part could be a little bit confusing because when you get into loops in Python, your counter variable, in this case j, does not start at 1. Counters do not start at 1. They start at 0. And so if I put in n equals 10, then j is going to go starting from 0 up to 10 plus 1. And actually, even 10 plus 1 we know is 11. It doesn't even go up to 11. It goes from 0 to 10. And if you take your fingers and start counting on your fingers 0 to 10, you'll need an extra finger somewhere, but you'll need to count that. 0 to 10, you'll have 11 items. And so that's the thing about for loops you have to be prepared for, is that for loops start counting at 0. And when it says range here, n plus 1, it actually goes up to the element before n plus 1 is where it stops. So it goes up to n. And here for the I loop, it goes up to n minus 1. Now, if you can get your head around the fact that the counter starts at 0 and not 1, you should be okay. But here is where we start inputting the values into the matrix. And then for fun, after we input the values, I just print out the matrix so that we can see it. Now we begin our actual GEM loop right here. And so I is the row index, is going to go from 0 up to n minus 1. And if any diagonal elements are 0, then we halt the program. A 0 was found on a diagonal element. If the program doesn't halt, then that means it comes down to this section here. Now remember, you can do any linear combination of two rows to create a new row. And the way that we're going to get zeros below each diagonal element is to first calculate a ratio. Now j here starts at I plus 1, so that's the row below the diagonal element, I plus 1, and goes up to, instead of n, it goes up to n minus 1. And so what we're going to do here is we're going to create what's called a ratio. We're going to take the element in a row below the diagonal, divided by the diagonal value, and then we're going to go across the entire row. So starting with k, goes from 0 to n plus 1. That's the entire row. We're going to perform this calculation here. And what that calculation is going to do is it's going to guarantee a 0 below the diagonal element, and then it's going to recompute a new number for each other element along the row, even the constant values at the end. So this line of code, all these right here, this is going to guarantee that we have what's called an upper matrix. It's going to put zeros below the diagonal. Now you're going to have to follow through the indices. That's the hard part, is following through the indices. So let's pretend that I is 0, which would be the first row. Then j actually starts at 1. And if this is a 3 by 3 system, then n would be 3, so it's going to go from 1 to 2. Not 1 to 3, but 1 to 2. And so the way that this works is this element here would be a10 divided by a00. So a00 is the first element in the first row. a10 is the first element in the second row. And then right here, a10 equals a10 minus ratio times a00. That calculates for that range, but k increases, right, from 0 to n plus 1. And so this goes all the way across the row. Once we have the upper diagonal matrix, or the upper matrix, we can then compute the solution for the very last value, So if we have n values, that means that the index of the nth solution is actually n minus 1. It's not n. This comes from the fact that we start counting at 0, not at 1. So we perform this division here, and that calculates the final solution for xn. And then we can start our backward substitution. So what we do is we store the next variable. Notice that it starts at n minus 2 and goes backwards to in increments of 1 backwards. It's actually not going to reach -1. It's going to reach 0, the number before it. Okay? And so first we store that, and then we start doing the subtractions. Remember, we've already solved for x sub j. So if we've solved for the last variable xn, then to get xn minus 1, we have to use xn, and that's where j is starting. It's starting at I plus 1. So we substitute that, we subtract it times the coefficient, and we follow through, and then we finally take and perform the division along the diagonal element, and that gives us the next solution in the system. So this loop right here is where the backward substitution comes in. And then finally, this right here prints all the elements of the matrix. Now, let me say this to be an encouragement. If that doesn't make sense, well, you're still okay, because this is not a programming course. However, it's just super useful to know how to write code that does all this, because linear algebra is one of those wonderful classes where you can program things and program all these algorithms out. But it's more important right now to me that you know how to do these by hand. But here's the code. Here's the code for you, so that you can follow through and try to figure out how the indices work first. So let's go ahead and run this. I want to show you that this does work. So I'm going to go ahead and run this. All right, now I'm going to have a 3 unknown system, and we're going to enter these one column at a time. So 1, -1, 3 should be the first column. 1, -2, -7 should be the second column. The third column should be 2, 3, 4. And then the column of coefficients should be 8, 1, and then 10. Then the matrix is printed out, so I know that I entered it correctly, and the solutions are obtained. It's the ordered triple 3, 1, 2. And so it's working.